Okay, we're going to rock on now, and our next speaker is M Burke.
Thank you. Hello. So I'm going to sort of continue on the theme that Bob has introduced to us about the Chert quarry clusters in Florida. My approaches are sort of a combination of what Bob is using with petrographic analysis, but in addition to that, I'm one of the folks in Florida who's trying to address the geochemical issues that Bob brought up. And so I'm going to try to sort of walk you guys through some recent developments and then what we're trying to do with geochemistry moving forward. I'm going to start off by parroting Bob a little bit about the quarry cluster method, but I'll keep that brief because Bob just gave us an excellent review of that. And then I'm going to talk more specifically about the Suwannee limestone formation and its exposures in North Florida, which is one of the parts of the quarry cluster method that has been somewhat neglected in the literature. Then I'll talk about some of the recent advances that have been made, particularly in North Florida, using the Chert quarry cluster method. And then we'll talk about the geochemistry as we, sort of the developments that we're all working on now to lead into Jessica's talk. So as Bob mentioned, the quarry cluster method was first developed in the 80s by Sam Upchurch and a couple of his colleagues, Knuckles and Strom. And it's still currently the prevailing method for sourcing Florida cherts, right? And that's for good reason, because it's a very robust method that's based on, not just petrographic analyses, but also on pretty substantial surveys that have gone on to build the method. In addition to that, it's tied very intimately to surface geology. And so we can see here this surface geologic map of Florida where the clusters overlap with the varying formations, okay? And so this method is one that is purely visual, right? And so it's a petrographic method. In some ways, it can be subjective in that sense, as Bob mentioned. But the one real strength of this model is that we're all sort of treating it like a framework. And so with that idea, right, we have this framework that we're constantly updating the substantive portions of. Okay, and so my research focuses more specifically on the Suwannee limestone, which is Oligocene in age and outcrops in several different places in the state of Florida. The Mariana limestone, or rather the Mariana quarry cluster, and the Byram limestone and Duncan church beds are what we would call Suwannee equivalent. So they're Oligocene in age, but they're a different formation than the stuff that I'm more interested in. We're very lucky to be in the Wacissa quarry cluster right now, and the predominant material that outcrops there is Suwannee limestone. In addition to that, there are exposures of St. Mark's limestone to our west, but as some of us at this conference have been talking about, finding outcrops of the raw material has been excruciatingly frustrating. So even though there's limestone available, there's not much in the way of chert. We know it's being used, but we just haven't found it yet. And so I'm hoping that some of the advances that we're making will be useful in rounding out what we know about the Wacissa quarry cluster. In addition to that, I've also been working in the Upper Suwannee quarry cluster, which is in the northern part of the state. The existence of this area as a place where you can find chert is based on Upchurch et al.'s, quote, geologic intuition, right? And so they use the fact that there's Suwannee limestone exposures in and around the Suwannee River as an indicator that the potential exists that there are chert exposures there. And I'm going to talk a lot more about that, our survey there and sort of what we found. In addition to that, the White Springs cluster just to the east is also a Suwannee cluster. The Brooksville cluster, that's the blue one in the middle of the state, in the central portion of the state, has Suwannee and Ocala formation materials in it. The Ocala stuff is somewhat restricted to the northern edges of the cluster. And then the upper Withlacoochee, which is the southern one there, is also a Suwannee and Ocala cluster. But most of my research has been focused on the northern part of the state because not much has been done other than some of the pioneering work that Jim Dunbar has done with collecting chert and recording lots of quarries in this area. So in terms of the specifics for Suwannee limestone chert sort of as a whole. It's what we would classify as a nodular replacement chert, and it's a microspherulitic chalcedony. So if you look at it under a microscope or even just up with some backlighting, you can see some of the fibrous structure in it. It's a diagenetically replaced fossiliferous grainstone. So what that means sort of in common terms, right, is that, as Bob said, the silica is being translocated through this in solution, and then instead of basically forming just chert, it's actually replacing the limestone material. And that's really helpful because that means we get fossil preservation. So these milleolith fossils, which you can see here, that Bob mentioned as well, are available to be found in the Suwannee materials, okay? But when the quarry cluster method was originally devised, they only had one chert sample or one chert quarry from the Wacissa cluster, of which they had 2 samples. And they used that to categorize what we should expect to find within the entirety of the Wacissa cluster. Similarly, White Springs had 2 samples, one of which was from agatized coral at Jim Mike Hill. And then from the upper Suwannee, as I mentioned, because it was more of a theoretical cluster, there were no samples that were collected there. So there really wasn't any information on the upper Suwannee cluster, very little information on the White Springs cluster, and even less on the Wacissa cluster before Jim started taking a look at it. And one of the things that I found when I began doing my research on petrographic methods for Florida cherts, I found some things that sort of stood out to me. So over on the left-hand side is a piece of debitage from Wayne Sink, okay, that has not only milleolids in it, right, which are the ones that are diagnostic of Suwannee chert, but it also has an orbitoid in it. Now this is not totally rare. Well, it is rare, but it's not impossible. But the concern is that that was never described in the Wacissa cluster before, right? And so if you were to find some of these orbitoids, you may misclassify them as, say, Ocala or something, which completely changes the picture on how you're interpreting how that artifact moved. Okay, and those orbitoid formations are quite common within Ocala cherts. Okay, and so the point I'm trying to make with this is that the more we sample, right, the more weird things we find, and the more we sort of start to refine this method, right? Because Sam Upchurch and those guys built this to be a work in progress, we're really charged with that. And the more we look, the more interesting new details we find that are helpful in determining chert provenance. And so within the Wacissa quarry cluster, where I've been working, right, as I mentioned, we only have one that I know of, right, recorded St. Mark's chert quarry, and that one is in inundated context in the St. Mark's River itself. Excellent quality material, it's really good stuff, but it's not really terrestrially visible in that I'm aware of. And so within the Wacissa quarry cluster, this is sort of a trend, right? We have a lot of outcrops of chert that are contained within river channels of the Aucilla or the Wacissa rivers. And in addition to that, we also have some terrestrial expressions of this too. So there's a lot of varied geomorphic contexts that are present within the Wacissa quarry cluster. Okay, and recently in Bob's paper in 2018, we expanded the boundaries of the Wacissa quarry cluster out into the Gulf of Mexico, where myself and several colleagues are, hello Sean, are actively out there working on finding more of these sites, right? This is all, of course, because of Mike Fott's idea about sticky up rocks, right? And that the rocks that stick up are the ones you want to make tools out of. And so within the Wacissa cluster, this site here is the volcano site, and the one on the other side is the Wayne Sink site. And so volcano has about 5 or so meters of topography. That's because of heaped up chert, whereas in Wayne Sink, we're in the bottom of a sinkhole and there's chert exposures down there. So there's a ton of geomorphic variability, which makes it really hard to predict where you might find outcrops of chert, okay? And that's sort of the task now, is trying to find a representative sample. But the problem is they're forming in so many different contexts that it's becoming increasingly difficult to model. In addition to that, some sites like 2.5 Fathom Quarry, which was recorded by Jim Dunbar, have this terrible mix of two things, where they're not only in a river channel, but they're also eroding out of much younger peat deposits. So that would indicate to me that there's probably tons of chert that's buried all throughout the Wacissa cluster that we have no idea where it is, okay? And that type of differential access is sort of what Bob was talking about, right? And so we can use this type of information to try to determine when these raw materials were available and when they sort of fell out of availability, similar to Bay Bottom chert, which is, we theorized was inundated and then therefore inaccessible. And so in addition to that, we also have several quarries that are offshore in the Gulf of Mexico. This is from a site that was just recorded within the last 2 years called Clint Scallopole. And this is an insanely large chert quarry with, I believe Morgan Smith says, millions of artifacts. I'll agree with them, there's a lot of stuff out there. But what's really interesting is that it's Suwannee chert, and it has a lot of similarities in the way that it's stained to some of the materials that we see within the river channels today, but this is not in a channel. So there's something going on here geochemically, and I know Jessica's going to talk more about this, but this has been sort of one of the major problems with me and my geochemical work, is that this weathering process becomes increasingly hard to navigate, right? And so it makes geochemistry a little tricky. So when trying to find these sort of like what it means to have representative samples from a quarry cluster, I went through the Florida Master Site File for the Aucilla Wildlife Management Area. And the site file says that there are 122 sites recorded as quarries. That's possible, but in going through all of those sites that are recorded as quarries, 17 of them had explicit mention of chert availability. And so if you plot those two, on the left-hand side I have all of the quarries, or quarries that are recorded as quarries in the site file versus ones that I'm confident are quarries. It provides a dramatically different interpretation of the lithic landscape, right? And so the answer to this is, well, like, why don't we just go survey, right? Like, it shouldn't be that hard, right? They're sticky up rocks, right? So the problem is, in the Aucilla Wildlife Management Area, this is the type of stuff that you're surveying through, okay? And oftentimes these sites can be somewhat low-lying, okay? And each of these localities has, high-quality chert, but to quote Clarence Simpson, he says that it's quite possible to pass within 20 feet of a mound and not see it for the dense vegetation, right? Which is very true. You sometimes have to be standing on top of a mound before you realize that you're on top of a mound out there. So what we've been trying to do to move forward in order to try to achieve this representative sample, or at least get the lay of the land for where these quarries are actually available, has been through the use of LiDAR. This has been used by FWC biologist Joe Davis, who's a really awesome guy who works out in the Aucilla Wildlife Management Area. And he's been using LiDAR in conjunction with a targeted and judgmental survey related to prescribed burns, okay? And so he's been using this to sort of try to push towards a landscape-wide approach. And so Joe will use this information, and then after a burn, he'll go out and try to find these sites when the vegetation is cleared off. And so myself and my colleague Morgan Smith have been working to try to automate this process, because you can't automate Joe Davis, right? So, but we're trying to duplicate him as within GIS. And so we've been moving forward with this topographic position index that essentially takes a DEM, or a digital elevation model, and compares pixels. So if this pixel is twice as tall as this pixel, then it'll flag that and indicate it to us. And so what we found is that we have about a 45% success rate so far with this topographic position index matching up with sites that are recorded as quarries within the master site file, okay? So we're hoping that, and I've talked to Jim about this, I'm hoping that we can use something similar to this to try to find the St. Mark's chert that we know is out there, that we see in the archaeological record, but we're having a difficult time finding any of the actual geologic sources for it. Okay, and so I want to move east now to talk about the upper Suwannee and White Springs clusters. And so before this summer, we had essentially only 2 sites that had been sampled within the White Springs and upper Suwannee quarry clusters. The White Springs one is the one over here to the right, and then the one to the left, the whole big Y-shaped thing, is the Upper Suwannee. And again, this is based on the fact that Suwannee limestone outcrops there. In general, the quarry cluster ends at the Ocala contact in the southern portion there, where we have our survey ending. You can see Suwannee River survey area end. And so before this, there were samples from Jim Mike Hill, which is the westmost green dot, and Little Shoals, which is in the White Springs cluster and is a series of rapids on the river. Okay, so this is what our understanding of chert availability in the Upper Suwannee River was, and particularly our samples. Like these are the only places we had samples from. And so after this summer, Chris Leidick and I canoed this stretch of river from Big Shoals all the way down to the confluence, and then we also did the Withlacoochee from the Georgia state line all the way down to the confluence with the Suwannee River. And the red dots here are some sites that were previously recorded. So you can see there were maybe like 10 or so, right, and maybe 10 or so in the Withlacoochee River. And over the course of our survey, we located over 60 new sources of raw material. Many of those, really the vast majority of them, were prehistorically utilized as well. So we found about 60 new chert and coral quarries in the Withlacoochee River and in the Upper Suwannee River. And so in the Withlacoochee River, again, this is the North Florida Withlacoochee, because there's also a South Florida Withlacoochee. So this is the North Florida Withlacoochee. So in the North Florida Withlacoochee, we identified these sites. They're predominantly of Suwannee origin, but there were some rare instances of Miocene-aged Terrea formation, and also Miocene-aged hawthorn opalines were present in here too, but in very localized geographic context. Now that's not mapped on the geology, right? So that's something that we weren't expecting to find, and something that was sort of unique. In addition to that, most of the material that we found in the Withlacoochee, as Bob mentioned, was agatized coral. And I have a couple images of the various types of coral on the top there, and then the cherts that we found sort of below that. Similarly, in the eastern portions of the Upper Suwannee River, we found right around 30 sites, and most of those were Suwannee lithologically. In addition to that, though, we did also find some instances of what we think is Miocene-age hawthorn opaline in there, but no real Statenville cherts or Terrea cherts. One other thing that we found during the survey was that after a certain point, we stopped seeing coral. And so we were GPSing all of the locations that we came across, and at these two blue lines on the survey is where we stopped seeing corals. So the suggestion that I think we're going to make when we finish analyzing all this data and all the samples that we collected is that we're probably going to put forth a revision to the quarry clusters in the northern part of the state, in that we want to separate the southern portion of the North Florida Withlacoochee and the western portion before the confluence of the Upper Suwannee River into essentially a separate cluster. So we'll probably make a Belleville cluster for the Withlacoochee that contains abundant corals and some cherts. And then the Upper Suwannee cluster will remain essentially the same, and we will extend the boundary of the White Springs cluster to the west to try to contain all of that coral. And so, as Bob mentioned, right, the whole point of trying to do that is to make it so we can move towards some discrete idea of where these materials are coming from. However, the coral is notoriously difficult to pin down to formation. And in addition to that, it's likely that even though we're looking at Eocene, or at Oligocene-aged limestone and Oligocene-aged chert, the possibility exists that we have both Miocene and Oligocene corals of the same genus, so we're not able to really divvy those up yet. But stay tuned, and we'll see what John Bryan is able to do with that. And so the question I have now that I get a lot, right, is what do we do with all these rocks? So within the Wacissa cluster, I've intensively sampled 8 different quarry sites, and so that means I have at least 50 samples from there for both petrography and geochemistry. In White Springs, I sampled 2. One was chert, one was coral. In the Upper Suwannee, I sampled 5. Those were all chert. And then in the Brooksville cluster, which I'm not going to talk about today, in the southern portion of the state, we sampled three of the sites that Chert originally sampled as well. And so that leaves us with 1,137 pieces to do geochem on and petrographic analysis. So that's what I'm going to be doing moving forward. But I wanted to take a minute to talk about the methods that we're proposing to use here. So the first is PXRF. We heard a little bit about that earlier today, and PXRF has sort of its pros and cons for this type of research. The first is that it's non-destructive, right, which is really helpful for archaeology because you don't have to break artifacts to use it, so that's really convenient. It is, however, going to be the least quantitative. It's difficult to know exactly how much of the material you're measuring with a PXRF, and that can be problematic for cherts where we're using very low levels of trace elements to make very big conclusions about where these materials have come from. And in addition to that, most of the raw materials in the state of Florida, once they're made into tools and put somewhere, experience some form of chemical weathering. Because I work in both inundated and terrestrial contexts, we see a ton of issues with staining of materials. And PXRF is going to be analyzing both the exterior and the interior of the sample. So that can be problematic, especially when we don't fully understand what's happening with the staining process. Now, it's sort of in contrast to that, we have neutron activation analysis, okay, which is exceptionally quantitative, very, very accurate, but it's also generally entirely destructive. It involves putting the sample into a nuclear reactor. It's really great for building a comparative database with your geologic samples that you don't care if they go into a nuclear reactor, but it's going to be difficult to convince somebody that putting a Clovis point in a nuclear reactor is the best thing for that artifact. So with that in mind, laser ablation ICP-MS and solution ICP-MS provide us with sort of a really interesting middle ground, okay, where we have a very high resolution mass spec, okay, that's going to be comparable to NAA provided that you use a quantitative entry method, okay. So that means putting artifacts into, or not artifacts, but geologic samples into solution. So we dissolve them with strong acids, and then we're able to take very small known quantity samples and run them through the mass spec. Now for artifacts, again, probably not going to let me dissolve part of their artifact and then put it through a mass spec. So the middle ground that we're finding with that is to use laser ablation, which allows us to create a very small ablation hole on the artifact, so we would consider it minimally destructive. And that allows the vaporized material to go through the plasma torch and into the mass spec, and then we can get some good data that way. And so these three methods sort of like, they all have their pros and cons, right? And the way that we're attempting to do it now is by building this comparative database with NAA on geologic samples. And now we're moving into doing a solution ICP-MS, which we've had some success with dissolving the Chert samples, which is a good thing. And so then after that, the following step will be to take that information and see if we can't make a calibration that will make XRF better for what we're doing, okay? And this is, it's not as though I invented these methods. We have a lot of folks who are doing some really good work all over the country with this type of stuff. I have a couple examples here. The first is from Ocala et al. In 2011, where they sourced 3 bifaces from the beach cache to Sentinel Butte Chert source, which was 19 kilometers away. And so that's sort of interesting because you would expect the caching behavior, they wouldn't be doing it so close to the source, right? And so, you know, in a study like this, folks may not even care to do the geochemistry because of how close they are to the source. My colleague, Andy Spear, has been working in Central Texas for a number of years now and has had success with sourcing Clovis points using LAICP-MS to both geographic areas on a large scale, so something akin to the size of a quarry cluster, versus occasionally getting really lucky and being able to source things to a much smaller scale. And then the last one that I always like to bring up, because it was always my favorite, was the Boulanger et al. Paper from 2015 from Paleo Crossing, where they had a successful sourcing of Chert from the Wyandotte Chert source. They sourced it from Ohio to the Wyandotte source, 500 kilometers away. But the concern is that the sourcing was done on debitage, and they later realized that there were contextual issues, so they weren't sourcing Clovis material. And so that's sort of like the cautionary tale is make sure, it's good to focus on diagnostics because you at least have some understanding of how old they are. Okay, and so within Florida cherts, we sort of have some problems with applying PXRF and geochemical methods. So the first is that we sort of lack any Florida-specific geochemical calibration. Okay, we can use comparator methods. You can use obsidian or basalt or something like that, but because they're so different lithologically, there's a lot of uncertainty that's introduced by that. And we're hoping that creating an NAA database will help with that. In addition to that, as I mentioned before, right, we're not exactly sure how much we're measuring. I think Jessica's going to talk a little bit more about pulse processing, detected elements, and detection limits. But oftentimes we're talking about parts per billion amounts of trace elements, which we can get with NAA and laser ablation, but we cannot get with PXRF. And then lastly, the superficial chemical weathering is, I think, a major barrier to this. So the staining process is especially common at inundated sites, and the chemical weathering is also disproportionately impacting earlier sites too. So the longer it's been sitting in the water, the higher probability that it will be discolored and chemically weathered. So sorry, paleo folks. And so to try to demonstrate what exactly is happening with the staining process, for my master's thesis, I broke, with permission, 110 artifacts from Wayne Sink and did PXRF on the inside and outside of each of the artifacts, and then compared the results to bone. And what I was able to find is that there were definite and overt ratio differences that showed that phosphorus, sulfur, manganese, iron, chlorine, potassium, calcium, chromium, and zinc were all impacted by the staining process. In addition to that, with the exception of calcium, it was an additive process. So what that means is we have the environment that the artifact is in actually contributing discoloration and chemicals and trace elements to it, which means that if we're going to use superficial methods like PXRF, we have to account for that. Otherwise, we're getting results that we really can't tie back to the lithology of the material. And so in thin section, right, we can see pretty clearly that the staining is also not purely superficial, right? So this suddenly now it becomes a barrier for subsurface methods too, things like laser ablation. Okay, and so as this stain diffuses through, right, we have a lot of oxidization and a lot of deposition of trace elements, and so this can provide some issues. So the way that we're trying to get around this is to build a small comparative library with INAA from across the state. So this allows us to control for exactly how much we're sampling and what we're sampling. So when we get geologic samples, even if they have weathering on the exterior, we can subsample from the interior to avoid as much of the chemical weathering as possible. This also allows for us to use scientific standards and calibrators with greater faith. In addition to that, because we're using both NAA and laser ablation, it allows us to avoid the weathered processes at the onset of the study and also to directly analyze them with laser ablation. So I have here an example of a thin section, and with laser ablation, we would be able to start a scan here and run it out. So that way we can look in real time as the trace elements change as we scan out. And so the goal then, right, is to take all this and make a PXRF calibration, right, curve of some sort for coastal plains cherts that will hopefully allow us to do some of this stuff with PXRF. And then in addition to that, we're going to take the NAA data that we have and use it to inform our solution ICP-MS information. So the first step now, because I've done some NAA, and I'm going to talk to you guys about that in just a second here. I've done some NAA. The next step is going to be to take all the ones I've done neutron activation analysis on and do them with every other method. So that way we can look at exactly how close we are, basically. And so to show you guys sort of some of the results I've had from statewide sampling, these are 10 samples from across the state in different places. And in each of these locations, we had a sort of presence and absence of certain elements or an orders of magnitude increase, right? And so from Jumping Creek, right, we had a spike in barium, a spike in cobalt from the lower Withlacoochee. At the Peace River, we had significantly more europium by a large margin than we do in most other places there. And similarly, from the Colorado site, there was a big jump in manganese, okay? And so within a site, in and of itself, right, we also have some degree of consistency. So this is normalized on, the top one is normalized on barium, but you can see that within a site there's anywhere from 50 parts per million barium to 500 parts per million barium. So when you only take one sample and say, oh look, the barium is like off the charts in this one, that must be indicative, like I just said a slide ago, you have to take into account the variation that exists within that outcrop. Okay, and so that being said, things like uranium will potentially have a little bit more use, right? There's some consistency across the whole of one intensive site, right? And so to wrap this up, what we're seeing is that NAA has some potential for this, and there's some consistency that is present within these chert outcrops, and the consistency may differ across the state. And so, but the biggest impact for me was this notion that within a single site, we had a very low coefficient of variation geochemically, and in the statewide sample, we had a high coefficient of variation. And that means that we meet the provenance postulate, which means we're moving towards this idea that there's actually less variability within a single source, which means that we should be able to geochemically characterize it. And so moving forward, we're going to begin addressing all of these things I talked about, including the superficial weathering, and then we're going to start moving on to doing minimally destructive analyses on actual artifacts and begin the comparison. Okay? And of course, in addition to that, we're also going to petrographically describe both the Wacissa cluster and the upper Suwannee clusters, so that way we can contribute to the visual methods as well. So I want to thank all these folks here, and thank you guys very much for your time. Yeah. Hey.